Hello, welcome. This is sort of a weird video, really. I've not done a video like this before. Well, I would say, with the whiteboard behind me, me waffling on about some random rubbish. That happens all the time. But in this particular video, it's just kind of an introduction to the course and pointing out a few things. So purely, you're probably just watching this video to waste a few minutes, which I don't blame you. Anyway, so this course, Mechanics Unit 1. Mechanics is very closely linked with physics. So this particular unit, M1, is closely related with physics first year, AS. Mechanics in that and the mechanics in this are very similar. However, we introduced something called vectors in mechanics, which is also in C4, which is actually an A2 maths topic. But obviously one or two things, small things, have changed from that, but generally it's the same. As I said, the only thing that's different really is we introduced something called velocity vectors, and that's what we're going to be going through in one of the next few videos. So I almost said in this video, so I'll just give you an idea of how it's broken down. So and how I'm going to be doing these videos. So the first sort of big bit is vectors, which I'm just going to, for that, instead of completely redoing the entire topic with the same stuff in the topic, I'm just going to link in my C4 videos into this M1 playlist. So it benefits you, you don't have to watch a video twice essentially, and it saves me a bit of time as well. So obviously time is cash, but I'm not making any cash, so unless you want to sponsor me, of course. So anyway, that's the vectors bit, and then we're going on to kinematics, which is velocity and time graphs, again a physics thing, but you just need to know a couple of things like what's the area under a velocity time graph, well, what's the velocity over time, what's acceleration, change of velocity, so therefore the area under it is acceleration. So that's just, again, a bit of background. So first year physics, that should be just pass you by. SUVAT equations, so if you're not sure what they are, basically you have your distance. Each of your SUVAT equation you have, we don't just come up with a name randomly. SUVAT, you have S for distance, U for initial speed, V for final velocity, A for acceleration, and T for time. And you come up with various equations that will help you to work out situations. And generally they're modelled by particles, which is what we're going to focus on in M1. And then the next bit is sort of equilibrium. So it's sort of resolving forces, really simple that. And moments, which is a little bit more complicated, but it's not that much more. Especially, it's more complicated in physics, I think. Again, I'll be linking in videos from my A2 AS physics playlist in this, where appropriate, instead of just repeating myself, because I probably was better last year at this. And dynamics, so this is force equals mass times acceleration, which I'm not sure, I might do another video, but it'll be the same stuff, so I probably will just end up copying it in. It's just the, so for if you're doing AS maths and you haven't done AS physics yet, this will just be passed by, but if you've done AS physics and you're doing AS for the maths, this is, or whatever, if you've done physics, it's force equals mass times acceleration, so there's resultant force, not just a force, equals mass times acceleration. There's various degrees on that. There's inclined planes, which slopes, which is actually, that's a key difference between this and AS physics. You have something called the coefficient of friction, which you don't do until A2 physics. However, in this concept of mechanics on rough inclined planes, we had something else, which is really simple. And it enables you to work out that backwards force up the slope that you never really did in AS, unless you did something under the AQA. And then we're going to be talking about momentum and impulse. As I said, for that I'm actually going to be linking in A2 physics mechanics topic, so I'm just bringing the videos from there. So there's only going to be a few new videos for this, and I think probably only one or two for mechanics, and I'll just link in the rest, so you just have to put up with the facts. I'm talking about AS physics or whatever it might be. The content is exactly the same. I'll point out, I might add a few videos in, because I'm lazy and say, oh, well, I talk about this, but it's relevant, so you just have to watch it and pick it out yourself, because I'm lazy like that. So, okay, right, got that out of the way. What I'm going to be doing in this video, so I'm going to be a bit of an introduction to the course. So that's how it's structured. There are 3 or 4 main bits to it. I'm just going to be going through some. Now, in this booklet, obviously you won't have this, but well, no, say you won't. You might do. I'm more than happy to give you sort of sheets of this for questions. I'll put questions on the sheet and obviously not copy it from this at all. And then we can try and help each other out with some questions. Well, help you out really. So the first little bit is quite relevant. It goes on just what I've said. This next page though sort of goes through some terminology. So I'm just going to hint at some terminologies. This is just a list that I've obviously created myself. Obviously, with just some key things that it might come across in terms of the questions, and you might go, "What the hell is that going on about?" So if something's rough, then obviously, if something's smooth, it's the opposite. Smooth's general. So it's got some. You have to put some extra force to overcome some other force, and obviously, other force is known as friction, which is force that opposes motion. Which again, done AS physics should be alright. Smooth, just the opposite of what I just said. Thin, so basically is something that has negligible thickness, so you can't really consider the fact that it's even close to thick, which I am, but never mind. Particle, so basically the difference, don't get too confused with when it says particle. In particle physics we're actually talking about the mesons, baryons, etc. But in this we're just talking about sort of concentrated mass, if you think, because we like to use balls. You know, take that from what you will. Lamina, so you may have heard this quite a few times. This is a lamina. It's just a thin, well this isn't thin, but you have a sheet that's quite thin, sort of an A4 piece of paper is a lamina, because it's a flat object, whose thickness is so small compared to its length, so this is very thin, quite long. Rigid body, so basically it's just something that doesn't change shape when you act force on it. Uniform rod, so this is where it's the equal, so basically it's where the mass is concentrated to the centre. Centre of mass is at the centre point, so you can almost assume it's a particle. Non-uniform rod is the opposite of that, where the mass is just spread out across the weight of the length of the ruler, for example. An extendable string, it's quite self-explanatory, it can't change length. And then obviously the extendable, which is the opposite of that. Smooth surface, kind of rough and smooth surfaces, what we just discussed at the start. Light smooth pulley. So a smooth pulley, actually, just go through that now. What a pulley is something like this. You probably won't have seen this. You won't have seen this. It's something that where you have a mass here and another mass here, and it's sort of like this sort of circle. It's not a very good explanation. This is a it's just a pulley, so it has something that a string can go around it. Obviously this is not jumping off, it should be attached to it, but it's just my poor attempt at drawing that. That's really it. Apart from that, as I said, all of them you should understand from your AS physics if you've done that, but that was just sort of a quick introduction to mechanics. So thanks for watching. As I said, it's been quite a weird video, because I just wanted to explain the fact that I put some AS and E2's videos in here, because I can't be bothered. Well, you know, waste of time on my computer. Putting up some extra videos that say exactly the same thing, I might miss out one or two things, so I trust my old self to deliver the videos. It's pretty good. So anyway, thanks for watching, and we'll see you in a video that probably has actually some theory in it. So, hello, this is actually an M1 video. It's probably the only M1 video that's actually got some theory behind it. Well, so the other ones do, but I don't say M1 at the start. Because I just copy them in from the other videos. So, just in one of the other previous videos, I did mention the overview of the course, so obviously I'm going to do that again. So what we're going to do in this video is, this is on something that we don't have in any other video that I've done so far. It's called velocity vectors. Fairly simple, it's not that much to take in. There's only 2 bits to this. So we're going to be looking, well, 2 main bits. There's a couple of individual subsections. Make it complicated. So there's 2 main bits, and then there's smaller branches in the big topics in this video. So we're going to be going over sort of bearings and sort of the speeds of objects. That makes any sense. It will do eventually. And then we're going to be calculating velocity given speed in a calculating velocity given speed and direction. So basically we'll be using some formula that don't want to give too much away. We're going to be using a formula, and I'm going to show you how you create that formula from what you're given. Okay? Right. So hopefully that makes some kind of sense. So speed of an object. Okay, so we're going to start off with something nice and simple, because we're all nice and simple people, obviously. So, that wasn't meant to be an insult, but it just happened to be. So say we've got the object going 3 meters per second in the x direction, or I is equal to 3 meters per second. And then in the y direction, I'm not going to draw it in 3D, so I don't need to put it flat. So in the y direction, or the j direction, we'll be saying it's going 4 meters per second. Okay, and you draw something like this. You want to resolve that force. You draw something like this. You can imagine either their forces or speeds. Doesn't matter. The principle of working it out is exactly the same. So we've got a formula R there. Alright, and we want to work that out. So what we do is we use our idea of, say this is R, yeah. Use a formula of the modulus, or the length, or the magnitude. The magnitude is, so this R has a formula 3I plus 4J. And to work that out, what you do is you'd square 3, square 4, which give you the square of 9 plus 16, which is square of 25. It's 25, so you square root that, so square root 25, which equals 5, therefore R has a speed of 5 meters per second, okay? So what we can say from this little bit of information we've just done, which is knowledge that we should already know, is the magnitude of a vector. This is a velocity vector, that's key. You can't do this with a directional vector, and we'll explain a little bit about that later on. So anyway, for the moment, you just need to understand that using a velocity vector, and I'll show you how we calculate one of them again later. The velocity vector, if you work out the magnitude of that, you will get the speed, because the velocity vector is to do with velocity. So if you work out the magnitude of that, just the magnitude, remember velocity has magnitude and direction. If you work out the magnitude of velocity, you said if we relate it to vectors and scalars, is speed. So therefore that's the speed, that's why that happens, and we can't just sort of giving you a bit of background, and I've not just said I'll accept it. And I've sort of am saying that. Okay. So that's how you work out speed. Right. So what I'm going to do now is relate this to something we call bearings. Now, again, this should be really simple in terms of, well, the bearings, but you should know what bearings are. So if we have that idea, but say we need to include the directions, for example. So instead of putting X, Y, and Z or whatever, I'm just going to put north, east, south and west. And say in the south direction, we've got a speed of, remember, you can relate these to I, J and K's. So the N, that's J. E, that's the X direction, so that's got a vector of I. And then this is negative J, etc. And that is negative I. So say we're going towards the X direction or the east with a velocity of plus 3 meters per second, and dragging down, they're going south with a negative velocity of call it negative 4 meters per second. And we want to work out the bearing and the resultant velocity or speed. So do the same thing that we did before initially to work out the speed or the resultant force. So we'll call this R. So therefore we said R was equal to the square root of 3 squared plus 4 squared. Now even though that's minus 4, don't take it away, because otherwise you'd be doing, for obviously some you'd end up with minus, you can't square root of minus, so this would be pointless. So you always keep them positive. Because the plus or minus just dictates the direction, and as we're working out the magnitude, we're not interested in the direction, so therefore we just include them as numbers. So do the same thing, so it's the square root of 9, 3 squared plus square root of 4 squared, which is 16. That still gets us a speed of 5 meters per second. So it's pretty much what we just did in the last video. In the last, not video, little section. So we know that's the speed, okay. So if we turn this little bit here into some kind of, because what we want is we want this angle theta. Because the bearing is, so if you have the bearing of something from north, and it was over here, you'd want the angle of all of that theta. So you'd want the big angle all the way from north to the line. But we can't do that because to be able to, yeah, we know that's 90 from north to east, that's 90 degrees, it's right angle, it's obvious. But what is this little angle theta? Now we can't work that out by any other method than basic trigonometry. So this is sort of an upside down right angle triangle, if you will. So what I'm going to do is sort of make it even simpler than it already is. So I'm going to draw, we just worked out the resultant velocity, which we said was, or the speed, which was 5 meters per second. Obviously you'd have to use that if you don't want to. And also we've got the height of the triangle, which is the south, which is 4 meters per second. And then we've got the base, which is, we said, was 3 meters per second. And if you relate this triangle to the one up here, then we want this little angle over here, theta. Now there's numerous ways you can do this. You can do this anyway. It's basic trigonometry after all. So what I'm going to do is use tan. So we say tan theta. So if you go SOHCAHTOA is opposite over adjacent, which is 4 over 3. So the tan theta equals 4 over 3. So therefore theta is the tan inverse of 4/3, which from my head is 53.1 degrees. So therefore that's theta. But that's not the whole of theta, remember, because we've got to include the bit from north as a bearing. So it's actually 90 plus, because we want all of that. So it's 90 degrees plus theta, which is 53.1 degrees. So therefore, if we work this out, it's 143.1 degrees as a bearing from north. Okay, so what we did there is we just worked this little bit out as we did before in terms of what the actual speed was and then in direction in the bearing. Okay, so that's just really simple sort of stuff. Hopefully that should be, it's nothing strenuous yet. But this bit isn't strenuous really. And mechanics isn't that bad. So like, it's sort of the same sort of, probably easier than statistics I would have thought. Right, okay. So, what we're going to do now is we're going to sort of keep that in your head, but we're going to sort of forget it for a minute. Okay, so back to, well, this is where it's a bit tricky because if you haven't done A2 maths yet, this is going to sound stupid, but if you have, for the benefit that I have, I'm going to do it that way just because it, you know, there's no really, the explanation is both the same because the principle is from C4 maths, so you know, if you're just doing AS further, then you'll be learning some C4 stuff here. Okay, so what I would, if you don't understand this, because I don't want to explain it again and again and again, or twice, I've done the vector equation of a line. That's in my C4 videos, so you just have to pop over to that one to understand where this comes from. But in essence, in the subject of that video, we said, okay, the vector equation of a line. So for the position vector r, which the position vector, for those that you are not aware, it's the vector from, yeah, it's just a vector from somewhere. So it's just a vector, a given vector. So that's the point of somewhere on a line or a graph. That's the position vector. That is equal to r0. That's the let's see. Wrong one. Sorry, I'm going to start giving you the wrong equation there. So that's r is equal to a vector a, which is just the vector from 0. It doesn't change. So I really shouldn't be doing this. So say you've got your axes x and y, and you start from the origin. We'll call it 0, and you go up to the line like that. And this vector, to get up the line, we call it vector A. So that's where this comes from. It's sort of from the origin to get up to the line. It'll be given to you. As I said, I do go over it in a bit better detail. You'll be thankful to hear in my C4 video, but I didn't want to repeat myself twice for obvious reasons. So that's how that's where that little A comes from. And we said that is added to lambda, which is just a magnitude of some sort of how many parallel vectors you go along the line, which is the next part, which is B. So this B could be, it's parallel to the line, so these little arrows I'm drawing on now, they're parallel to the line, but they're not going through it, obviously, but they're not cutting through it either. They're not on the line, but they're going in the same gradient, essentially. So this is B, that's the parallel vector. Okay, so that was just a bit of C4 stuff. As I said, there's a proper video on that, so just waffle on about anything. So why am I showing you this? Well, this is very similar to what we're going to be talking about next when we go on to talk about, oh sorry, my brain's just gone funny. When we go on to talk about finding velocity given speed and direction, etc. So this, as we said, this position vector that changes. This A is a given vector that doesn't change. That's to get to the point on, that's point on the line essentially, and this lambda is a magnitude, and B is a parallel vector to the line. So how do we relate this to this kind of vector that we're going to talk about now? Sorry about that. Well, not actually. That wasn't sort of the idea for that line we were going through. Which actually calculating velocity given speed and direction. We're calculating velocity as a rate of change of position. Okay, so that formula we just created, the idea was the same, but I'll just give it the wrong title. So we said the R is equal to R0, so the position vector is equal to the direction vector plus VT or TV or whatever you want to call it, time being the changing factor. So if we wanted the velocity, it's the rate of change, so don't get confused, we're not differentiating anything, all we're doing is the rate of change is over time, so we're just dividing, we have a time factor in there. So if we want velocity on its own, we velocity is equal to R0, so R, take R0, over T. That's just a simple rearrangement of that formula above. So we took R0 for both sides and divided both sides by T, and we came up with this equation. Okay, so that's a very simple rearrangement really, I don't need to go too much into that. But as again, it's just a simple case of remembering that formula and then knowing to apply that one to where you need it. Okay, so what we're going to be doing now is we're going to be calculating velocity given speed and direction. Now, well, no, that was velocity, but we're going to be looking at this velocity in terms of the velocity vector and what we mean by that. So the best way to do this is probably through an example. So I'm just going to pick an example out of here. Just give me a second. So this is, if you've got one of these booklets, it's the Edexcel Mechanics 1 booklets. But again, if you're not in the class, and probably something tells me you might not have this. Oops, sorry, going too far there. Right, okay. These are some good examples there. Right, so we said, really going, don't really need to work that actually. It's not really much of a backup knowledge to this really, I was just trying to think of a good way of presenting it to you. I should have thought about this before, but hey ho, never mind. So I'm just gonna nip through these a second. Yeah, there's no real backup to this. I'm just going to give you it and just sort of explain it. Okay, so this is just a formula you're just going to have to understand. So velocity vector, and when I explain, so I'm going to give you the formula and I'm going to explain it. And when hopefully it become apparent, that's a speed over magnitude of the direction vector. So the velocity vector, speed over the magnitude of direction vector. Oh, this is the length, or if you want to, whatever you want to call it, times the direction vector. So what we're essentially doing, because we want to know the velocity vector, so we're not 100% on what exactly is the velocity vector. Now we said, if you remember, the magnitude of the velocity vector is speed. Okay, so what we're doing essentially here is working out a proportion. So saying, okay, well this is the magnitude of the velocity vector and this is the magnitude of the direction vector. They're going to be in some kind of proportion. They're not going to be changing proportions. One's going to be sort of like double the other one, for example. Double the direction vector. What we're essentially using this formula to do is to turn the direction vector into the velocity vector, and we do that by, because we look at the velocity vector and we look at the direction vector, and we say, right, what do we have to do to get from the direction vector to the velocity vector? And the simple answer is working out the scale, or the proportion, if you want to think of it like that, in terms of the magnitude of both of them. So this is the magnitude of the velocity vector and the magnitude of the direction vector. In speed, I could have just easily written the magnitude of the velocity vector, but this would have been hard considering the fact that when we are trying to work out the velocity vector, it's quite hard to work out the magnitude of something if you don't have it. But we will be given a speed, so that's why we write speed and not magnitude of the velocity vector. But so essentially, what we're doing is working out we're working out the proportion of the two events. So saying, okay, well if the velocity vector is double the direction vector, then what we'll do is, okay, so the speed might be 14 and the magnitude of the direction vector, it might be sort of I plus j. It'd be square of 1 plus the square of 1, which is the square root of 2. Oh, that's a better example, actually. If speed was 2 root 2 and that was 2 root 2, sorry, then the proportion would be 2, so the velocity would be double the direction vector. So you double each of the individual terms in the direction vector to be able to get the velocity vector. Now this is a lot more obvious when we start to go through some examples. So I'll go through some now. So you keep that on your board. That's a good thing to remember. I try to explain it in a way that helps you remember rather than talk you through it, because I think, it's got a bit lazy, to be honest, and I don't want to confuse you. But obviously I haven't so far, so it's pretty good. Okay, so exercise 8.3, question A. So as I said, this is just a question. We've got some more theory to do, actually. Might change my mind, I don't know. No, we don't have any more questions. Theory to do. So that's the theory for velocity vectors. We're just going to be going through some questions now. So we're using this idea, the equation above. What I always do is write down the individual bits of information given in the question. But seeing as you can't read this question, then I'm just going to give you the key bits of information, and we're going to work through it. So we're told in the velocity, the speed, is 10 meters per second. And the direction, I always put directional vector rather than direction. Is equal to 3I take 4J. Now it is critical to realise when you're working out the magnitude of something, obviously you use Pythagoras' theorem of a squared plus b squared, square root of that, and that gets you the magnitude of it. Even if there is a minus, you ignore the minus sign, you keep them positive, because when you square something it's going to turn out to be positive. And obviously that'd be, you could end up with a negative square root, which you could do if you did, if you were doing FP1, but this is M1, not for the pure 1, so it's a little bit different. Okay, so that's directional vector. So the only thing we don't have in this, you could do it either way now. You could rewrite this equation with these two bits in it, or if you wanted to save yourself some time, I just work out we're missing out the magnitude direction vector now. We don't really need to write it out to realise that. Hopefully. So therefore what we do is do the standard thing when you work out the magnitude of something. So it's 3 squared plus 4 squared, which is 9 plus 16. 9 plus 16 is 25. Root 25 equals 5. So it's 5 meters per second. Okay, that's the magnitude. Oh, you could just put 5. It's up to you. Probably the best, even it as that. So therefore, we know the velocity vector is 10 over 5 times the direction vector. So I'm going to write that in instead of just writing 2 times. So it's velocity vector. Remember, it is the velocity, but it comes out in i's and j's, so we can't write it as velocity really. And so that's 10 over 5, which is 2 obviously, times 3i minus 4j. Okay? So therefore, you expand this out. Now I'm just going to assume that will just change to 2. So I just write 2 underneath it times that. So I'd have to write it out twice. But obviously you would if you were in the exam. So expand that out so you get 6i, take 8j. And that would be your velocity vector. Alright? So what I'm going to do now for you is just going to do some individual questions. So you get the idea of that. Right, so I'm going to put some, label some questions out with key bits of information. So I will end up rubbing them out, but then I give you a few seconds so you can pause the video and have a quick go at them. I'll leave the equation above, but if you want to ignore that, then you're more than welcome to. And I would quite strongly advise that, put it in there. That's just, in case you go, okay, what's he going on about now? Alright, so as I said, I'm not going to go through all of them because they are quite repetitive and you'll end up saying the same thing anyway. But I'll talk you through the key bits of information if you can't quite read it out. And I'm just, instead of putting direction vector equals, I'm just going to put the key bits of information because, using a formula above is not going to have anything else. You're not going to be given the velocity vector. You're going to be given everything. Anyway, so, shut up now. So C. The first one, 15 meters per second in the direction minus 4i plus 3j. C is 7.5 meters per second in the direction of minus 6i plus 8j. D, the speed is 5 root 2 meters per second in the direction of I plus j. Okay. E, 2 root 13 meters per second in the direction of minus 2i plus 3j. Okay, so I'm just going to leave you to have a go at them now. So if you want to have a pause video, and we'll go through them in a second. Now, obviously, you're more than welcome to just sit back and let me do the work, but I think you've had enough of my voice for a few minutes, so I'll just pause the video and let you have a go at them. Okay, so we're going to go through these now. Hopefully you've had a go at them. So what I'm going to do is I'm going to leave all of them sort of on the side there, but this little space here, I'm going to work through each one and then rub it off. Okay, just so you get an idea of how we're going through them. Alright, so the first thing that we need to do is, the only thing that we don't have is work out the magnitude of the direction vector. And obviously each one of these are the direction vector, and they each have a coefficient. And the coefficient of I and j is all we're really interested in. So what the first one is it's not minus 4, it's 4 squared. Works out the same. So 4 squared, which is 16 obviously, plus the 8 squared, which is 64. So therefore it's 16 plus 64, which is 80. Make sure I'm not going completely insane. 16, 64. See, I can't even type in my calculator, bad as that. 80, yeah. So that's just root 80. Which you can leave as root 80, or you can change it to root 20 times root 5, which is 4 root 5. Okay. Root 16 times root 5. So that's the magnitude of the direction vector. And obviously we just put in what we've got, all the things we need to know now. Obviously they're already listed for you, but I would have wrote them down in sort of the list form. So therefore we could say the velocity vector, that's equal to the speed, which we know is 15 meters per second, over 4 root 5, and that is times the initial direction vector of minus 4i plus 8j. Now you would work out, don't forget those little dashes underneath the i's and j's, so it's 15 over 4 root 5, which is 3 root 5 over 4. So I've done it in my notes. So that's equal to 3 root 5 over 4 times minus 4i plus 8j. And you would just expand that out. So the 4's would cancel on the first one. So it's just minus 3 root 5i plus 8 times 3 root 5 over 4. So that's 8 times 3 is 24. So it's 24 over 4, which is 6. So it's plus 6 root 5j. Okay, so that's your answer for the first one. Alright, so let me just double check that I'm not gone completely insane just yet. Yeah, that's right. Oh, I've not copied the one out correctly, actually, but that works for that one. It's a bit iffy on that, sort of, really, because I've not copied the question out right of the book, but as I said, it didn't really matter, that's how you'd answer that question. You answer the questions in exactly the same kind of way. Alright, so that's the answer for B. Just rub that off now. So right, rub B off because we've done that. So, for that you get a mark for using, working out the, you had to work out the magnitude of the direction vector, and then another mark for putting it into the formula, and then that mark could also include getting it right. So really there's only 2 marks per question. So use the same principle for this. So the first thing we want to do is work out the magnitude of the direction vector, which is 36 6 squared plus 64, which is root 100, which is 10. So therefore what you do is okay, apply it to the formula above. So it's the speed, which is 7.5 meters per second, over 10 times minus 6i plus 8j. Now you could write that as, so that's 0.75 times minus 6i plus 8j. I'm going to leave it as 3/4, so keep it as a fraction, times minus 6i plus 8j. Now I haven't done it in this question, I just want to point something out before I simplify that. You've got to be careful. If you're given the speed in meters per second, for example, you need to keep the velocity in meters per second. You can't change it to kilometers per hour or anything like that. So if you've done physics, that'd be obvious, but you need to keep it something we call SI units, or standard instrument units. I think it's that. Anyway, SI units, I'll just pretend I didn't say the other thing. Anyway, so that's minus 18 over 4i plus 8 times 3, which is 24, over 4 plus 6j. Okay, so that's your answer for C. So you can see we're getting quite a nice idea going. I mean, once you're getting the swing of it, these become very easy indeed. Okay, the next one, 5 root 2, I'm in the direction of I plus j. So therefore the direction vector is just 1 squared plus 1 squared, and square root that, which is just root 2. So that's the magnitude of the direction vector, which is root 2. Don't really need to only working out because it's nice and simple, that one. So it's 5 root 2 over root 2 times the direction vector of I plus j. So the root 2's cancel out, so it's just 5 times I plus j. Remember to keep the little dashes underneath. So we expand that out, then it's just simply 5i plus j. Now, I haven't done it in the previous 2 questions, I really should have done. Now that'd be your answer. I've kind of simplified it down because I didn't want to keep writing this. This is what you should really write. So you should write the velocity vector, or the velocity, is equal to 5i plus j, or 5j, sorry, or whatever it may be. And then you write meters per second next to it, because that velocity, that's a velocity, it's not a direction vector anymore. So you need to put meters per second at the outside of the vector. Now these really should have meters because they're direction, so only have direction to the length. So you put meters really, that's a standard one. Okay? So that's question D. Question E, similar sort of thing again. So you work out the magnitude of the direction vector, which is 2 squared plus 3 squared, which is 4 plus 9. 4 plus 9 is root 13. Can't do anything with root 13. And then you do 2 root 13. You apply the magnitude of direction vector, which we just said is root 13. So 2 root 13 over root 13 times the direction vector, which is 2 minus 2i plus 3j. Now, it is key actually to remember, because you have the i's in the x direction, so j's in the y direction and the k's in the z direction. Even if it is quite tempting because we've got minus 2i plus 3j to go, oh, that's not how maths really like, it's not how I like it to look. I agree with you, it looks stupid, but that's maths for you. So you always keep the i's first, then the j's, then any k's if you have any. So that's just a key thing to point out. Now the root 13's cancel out obviously, so it's just 2 times minus 2i plus 3j. So therefore you expand that out, that's minus 4i plus 6j. Okay, now as before, you would write velocity equals that in meters per second. But I'm not going to do that because tedious really. So that's the last bit really of velocity vectors. We'll go through a few questions. So what I'm going to do now is just going to give you a quick recap of what we've done in this video, and then just going to go through a few questions as well, in terms of using the other thing that we learned about. So the first thing we talked about obviously was the course. That was in a different video, but that's how I've come across it because I'm lazy. So after that we talked about the, oh my god, what order we did it in now, because I did it yesterday, so I need to know the order. So we talked about the bearings and speeds of objects, and then we just talked about the equation related to the vector equation of the line. We came up with the equation for the velocity vector, and we rearranged that and we said, okay, you could have the velocity vector as a rate of change. And then we talked about speed, calculating a velocity vector given speed and direction. We just come up with that formula on the board, and I tried to explain you went from a direction vector to a velocity vector, so you needed to work out the ratio of one to the other, so you could times the direction vector by that ratio to get the velocity vector. So that's all that we've really done. So just to recap, we went over the speed, which was just the magnitude of the velocity vector. We talked about looking at bearing, which is GCSE stuff really, but we had to used a bit of trigonometry, just took GCSE stuff a bit further, which probably should have done if you I'm assuming you're just doing AS Maths now, as a first year person. So you just apply GCSE knowledge really, nothing more than that, so it's fairly easy. And then we looked at the equation of the line. We said, okay, we can apply a vector equation of a line, we can apply that to the velocity vector equation, rearrange that to get t on its own, v on its own, so you get velocity as a rate of change of the directional vector. And then we just went on to talk about how you work out the velocity vector. So using that idea, but going, okay, there's a ratio from going from direction vector to the velocity vector, so you times the direction vector by that ratio. So I'm just going through the recap twice because it's just a load of words I'm throwing at you, and I'm trying to hope you understand it. Alright, so as I said, that was a nice quick recap of what we've done. So I'm actually going to yeah, we'll go through a few questions. So this is exercise 8.4 in your booklets if you've got them, but if not, you know, it doesn't matter. So I'm going to write that formula on the board, and then I'm going to do what I did before and give you a few seconds if you want to have a go at these questions. So the first one, A, even though I'm going to go like A, J, K or whatever, it's a bad example, A, F, E or whatever, I'm not going to do it necessarily, it's not going to be A, B, C, D, for example. These are just, I'm labelling these questions directly out of the booklet, so if you do have the booklet it's helpful, otherwise it's just a few questions. So, we're told to find what R is, and we are given what R0 is. So if you remember our equation of the line was R equals R0 plus VT. Okay, so that's, we've got what R0 is, which was 2I. V was I plus 3J. And we said T is equal to 4. Another one like that. So we want to know, we know what R0 is, the initial speed is 3I minus J, and V is equal to minus 2I plus J. And this is it when T is equal to 5. So they're fairly simple. D, find R0 if R is equal to minus 2I plus 5J. This exercise really is just making sure you understand this formula. I'm rearranging it really. And V is equal to 2I minus J. E, E. We want to know what V is. R0 is 2I plus 2J. R is equal to 8I minus 7J. And T is equal to 3. Okay, so that's quite a nice, I mean, I'm not giving you too much information there. Alright, let's be having a go at. But there's one more that no, actually, I'll leave it at that. I'm going to put one more on, but I think that's enough torture for you. So, as I said, you can either have a go at them, or if you can't be bothered, or if you've had enough of maths, I don't blame you, to be honest, because you've been listening to me, so it's hard enough as it is. Oh, sorry about that. Yeah, so I'll just give you a second, however long you want, to have a go at them, and then I'll come and help you out if you get a bit stuck. Okay, so just give you a second to pause the video and have a go at them.